In this lecture, we are going to discuss on strength of materials and theories of failure. In the last two lectures, we have seen that because of different kinds of loads, how the stresses are developed and how to calculate those stresses. And after that, we have seen that if we know the stresses acting on an element, then how to find out the principal stresses from that stress element. Now in this lecture, we'll see what we actually mean by strength of materials. Here you can see that this is an arrangement of a simple tensile test. Here this is the specimen and L0 is basically the gauge length, and as gradually the tensile load is applied the two ends in a tensile testing machine, then if we plot the engineering stress versus engineering strain, then we'll get this kind of a diagram. In case of typically low carbon steel or mild steel, you can find a definite yield point, but in case of ductile materials like aluminum or other kind of materials, you do not find such a specific yield points. So in those cases, basically corresponding to a particular strain value, which is called a set, and corresponding to that set, a line is drawn parallel to the origin of the stress strain diagram, and that line cut actually at a point on the stress strain diagram, and that point is called the proof stress, and this point is taken as the yield strength. As you already know, that yield strength is basically a point from which we can consider that material will not further behave as elastic material. That means up to yield point, material will behave like elastic material, but above yield point it will not behave like elastic material. That means there will be permanent deformation occur in the material. So yield point is a very important point from the point of view of the design, and that particular stress corresponding to yield point is called the yield strength of the material. Okay, so this is a specific stress value which actually indicates that after which permanent deformation starts in the material. If we consider the failure of a ductile material, that yielding is considered to be failure of the ductile materials. That means if the material has not been yielded, then we can consider it okay, it is within elastic yield limit, that means it is within elastic region. But if it is above, if the stress acting on the material is above the yield strength of the material, then it is considered that material is failed. Okay, so in case of ductile material, it is not that it has to be fractured to fail. It is basically plastic deformation. When it starts, we consider that the ductile material fails. Now you see another very important point in the stress strain diagram, which is called the ultimate tensile strength point. So this is the point where maximum stress occurs in this engineering stress strain diagram. Here you can see at this point basically neck formation starts. Here you can see a particular cross section, suddenly its cross sectional area decreases. That formation is called the neck formation, and ultimately it causes to fracture. But this is the point where the engineering stress is maximum, and this particular point is called the ultimate tensile strength, or simply tensile strength of the material. So by tensile strength is again a very important point, specifically for those who do not have specific yield point, or do not for the brittle materials, where the maximum stress in the stress strain diagram is called the tensile strength of the material. Okay, so these stress values, like corresponding to ultimate point or corresponding to the yield point, they have significance in the design, and that is why these specific stress values are called strength of the material. So by strength we mean specific stress values and those are basically experimentally found and listed in the material handbook. Here you can see another strength value, like the fracture occurs at this strength. This is called the fracture strength of the material. So in this way we get different strength values of the material. Okay. Here you can see for a brittle material the stress strain diagram is almost linear, and maybe a very small amount of plastic deformation is also possible before fracture. But this is the point where the engineering stress is maximum. So the fracture point is same as the tensile strength point. So this is the tensile strength of the brittle material. Is a very important stress value. So this strength is very important. Okay, tensile strength or the ultimate tensile strength of the material. Now, after all these knowledges of principal stresses and the strength of the material, now we are in a position to see the theories of failure. Okay, so these are basically some guidelines by which you can dictate whether under certain load a component will fail or not. Or before designing a component, we have to check with the theories of failure that this is safe. So some of the importance of the static strength values, already we have seen that from the tensile test we get the strength values, right? Like yield strength of the material or the ultimate strength of the material. This data we get from the tensile test of the material, and these having a very importance in the design. Usually necessary to design using published strength values. Okay, so these strength values are published in the material handbook, and using these values, that means the yield strength of the material symbolized by SY, or the ultimate strength of the material symbolized by maybe UT. So these are strength values we get from the tensile test material, and those are published for all the materials. Okay, and these are very important. And remember, these are static strength values. Okay, that means the load that is applied, a gradually applied load, those are basically kind of for the static design we use this data. Now experimental test data is better, but generally only warranted for large quantities or when failure is very costly. That means suppose a component is not a simple component like a tensile test whatever we have done, or the loading may not be so simple like whatever we have given in case of a tensile test. Okay, so actual component may be very complicated in shape, loading can be of a combined in nature, so different kinds of loading are possible. Now for the same material, if we make a tensile test specimen and do the tensile test and you get the strength values and you compare with the actual shape of the material and the actual combined complex loading, then this is what is the theories of failure idea. But actually if you want to know that because of this kind of loading of this particular shape, you have to experiment or you have to test with this particular shape with this kind of complex loading. But what people do, they actually predict the failure of this material by comparing it with the same material in a tensile test strength values. Okay, so this is what is the idea of the failure theories. That is why it has been told that experiment test data is always better. If you do the experiment of this actual shape and with all this combined loading, definitely it is better. But if the number of quantities are very large, okay, then it is okay. The similar kind of shapes and similar kind of loading, if is coming on a component, and the number of components are very large, or the process is very costly, okay, where your prediction should be very accurate. In those cases only we do the actual test or actual experiment on the actual shape and the loading. But in all of the other cases, what is the general tendencies is comparing this kind of thing with the same material, tensile test, strength values, and using the theories of failure. So methods are needed to safely and efficiently use published strength values for variety of situations. So we have understood, okay, there must be a technique by which it is possible to predict the failure of this complex shaped material with a combined kind of a loading with a simple tensile test of the same material strength values. Then how to relate these two is what is the whole motivation of studying the theories of failure. So theories of failure actually giving you the idea or guideline how you can compare this with these strength values, simple strength values that we get from the tensile test data. Okay, so that we'll be safe and efficiently we can compare. Okay, now you just consider the tension test that you have just seen, where uniaxial stress element, right? Here this is the component of the test specimen, and you are applied this kind of uniaxial load. Okay, so the failure of this particular component predicting is not very difficult, because you know the strength values, that means the yield point. Okay, so if the stress developed within it, is sigma, then that sigma must be equal to that strength value divided by some factor of safety or safety factor. So n is what? N is safety factor, so that your design is safe. So sigma is equal to S divided by N. This is what is the simple idea of the design. So the safety factor is what? The strength value divided by stress. This is a very simple idea since the shape of the component is very simple and the loading is very simple, which is uniaxial, and that is why it is very easy to predict that when the material will fail. Okay, and we can easily find out the factor of safety. Now consider multi-axial stress element. The practical situation is already you have seen the complex kind of a shape of the material of a component, machine component, and it is by the complex kind of a loading. That means combined loading, different kinds of loading that we have seen, all these may be in a combined form. So because of this combined loading and a complex shape, at a particular point the stresses in general will be the general state of stress. Okay, so here you can see the general state of stress, it is possible. Okay, so now the question is, if the stress is a general state of stress, then how can you compare that general state of stress with a uniaxial data that we do in case of a tension test? Because we have already told the whole idea of the failure theories is to somehow compare this general kind of a loading, and because of that the general kind of a stress that will be developed is somehow compared with only the tensile test data that we are getting, like SY in case of a ductile material, S ultimate in case of a brittle material. So this data we get from the tensile test, and which is very simple uniaxial stress element. So how these two are related, so that efficiently we can predict even in this complex kind of a loading on a component. So now try to see one analogy, and through which you'll try to understand. Let us consider that this lifter is lifting a load of 50 kg. Okay, now you see the lifter here also is basically lifting total 50 kg. Here you can see 15 kg is here, 25 kg is here, 10 kg is here. Total is 50 kg. Now you tell me that in these two cases, are these two cases are same, or do you think that the stresses acting on the different parts of the body will be same? Definitely your answer will be no, because here the load distribution is different from here, but the total weight is same. The idea that the failure theories gives is exactly similar. That means in case of a simple tension test, suppose P is what is the load that is applied in the simple tension test, and because of that we are getting certain strength values, and what we do, we are comparing with this different general kind of a loading. Here you can see different kinds of force and torque are acting on a machine component, and because of which at a particular point what are the different stresses that will act somehow is compared with a simple tension test. So directly these things are analogous. Okay, so definitely we are not going to get the exact prediction because these two situations are not same. That it is quite intuitive. Similarly here, these two situations are not exactly same, but we want to predict in this way so that we can save a lot of time and a lot of money, because to actually predict this situation you have to make experiment with this actual scenario. But instead of doing that, if we use this tensile test data which already been published, then it will be much easier. But we have to be very careful that our prediction should not be far away from the actual. So that is why we have to efficiently predict, and that is why we will see that there are certain failure theories, and already we know none of the failure theories are accurate, because it is not possible to compare these two. They are not accurate, but they are used to save money, save time, save material for that. Okay, so we'll see how different kinds of failure theories are proposed and how to use them. So failure theories propose appropriate means of comparing multi-axial stress states to single strength. So this is the main thing. So failure theories propose appropriate means of comparing multi-axial stress states to single strength. Single strength where from you are getting? From the tensile test. And multi-axial state of stress where from you are getting? Because of the complex kind of a loading that is acting on that machine component. Okay, so how to compare them, how to relate them, how to predict them, their failure of the actuals is done by the failure theory. So usually based on some hypothesis of what aspect of stress state is critical. This is a very important thing. What aspect of the stress state is critical, that we'll see in different failure theories. You will gradually understand this concept. Now some failure theories have gained recognition of usefulness for various situations. Okay, depending upon the different situations, depending upon the practice from the history, some of the failure theories are very popular and commonly used. So now once again recapitulate that what we are going to do. Suppose this is a machine component and it is loaded by different complex loading that you can see in general. Then what? So loading will be given to you. Then what you have to find out? At a particular point you have to find out its state of stress because of loading, using the basic laws of strength of materials that you have seen how to calculate stresses. After knowing the stresses acting at a point at different direction, its normal and shear components, what we can do, we can find out the principal stresses, that is sigma 1, sigma 2, sigma 3, that you can see. Okay, so principal stresses are the stresses, normal stresses where there is no shear in those planes. Okay, so we can find out principal stresses. Once we know the principal stresses at a particular point, then we have to use the failure theories to predict its failure. Okay, so now we have already done up to this much. Now we'll see what are failure theories. Okay, so again we have already understood that failure theories compare the certain aspect of the stress acting on a particular machine component, and that is compared with the strength values of the simple tension test. So the aspect can be stress aspect, that can be strain aspect, can be certain energy. So there may be different aspect of stress that is considered in different failure theories, but in all cases it is always compared with the data in the simple tension test. So what is simple tension test? Here you can see this is the sample, P is acting, let us consider one element, it is a uniaxial element, so stresses are P by A. This is very simple. You can also draw the Mohr circle of that. So Mohr circle will be what? Sigma x0, tau 0, so one point is 0 0 and another point is sigma comma 0. So now you can draw the Mohr circle, and from the Mohr circle you can see here is the tau max, right? So shear stress is what? If this value is sigma, that means this sigma from here to here, this is nothing but the radius, so tau max is equal to what? Sigma by 2, that you can see, right? So from the Mohr circle you can see the maximum shear stress that will be developed in a simple tension test is equal to sigma by 2. We can also find out the energy, strain energy density, that means strain energy per unit volume up to the yield point. If you consider this area, that will give you the strain energy per unit volume. Okay, so some of the important point up to yield point, you know, stress is proportional to strain. So E is the Young's modulus or modulus of elasticity. Strain energy is half into stress into strain into volume. Okay, and strain energy density is key, that is strain energy per volume. Okay, so half into stress into strain. And now strain you can write as sigma divided by E. So if you put this as sigma divided by E, it will become sigma square by 2E. So we can see the strain energy density is equal to sigma square by 2E. Maximum shear stress is sigma by 2, and strain energy is half into stress into strain into volume. So these are the important information. Now at the time of yielding, see why yielding is very important, because in case of ductile materials, yielding means the failure starts. So that is why yielding is a very important, and it is a point where we consider that ductile material fails. So that is why yield point is a very important point, because before it is elastic, and after it permanent deformation starts, that means the ductile material fails. So maximum normal stress that can be allowed in a ductile material is what? That is sigma is equal to SY, which is nothing but the yield strength of the material, right? Yield strength of the material, SY. Now, so the maximum shear stress is what? So maximum shear stress corresponding to yield is what? Maximum shear stress corresponding to yield is that sigma divided by 2, and that sigma is what? SY. So SY by 2 is the maximum shear corresponding to yielding of a tensile test specimen. Okay, so SY by 2 is the maximum shear stress. Now similarly maximum strain energy density is what? So that will be again corresponding to yielding. So when it will be corresponding to yielding, what is sigma? Sigma is SY. So it will be SY square by 2E. That is the strain energy density corresponding to yielding. So here you can see some normal stress value, maximum shear stress value, and the strain energy density value corresponding to yielding. Okay, these are the different quantities important in the different aspects of the failure theories. Now first failure theory that we learn is the maximum shear stress theory. Now according to the statement of this theory, you see the yielding begins when yielding begins means kind of a failure starts of a ductile material. Okay, so yielding begins when maximum shear stress in a stress element exceeds the maximum shear stress in a tension test specimen of the same material when that specimen begins to yield. That means, suppose a component is there and which is under certain general kind of a loading, and because of that, if we find a point where maximum shear stress is same as the Sy by 2, because Sy by 2 is what? That is the maximum shear stress in case of yielding of a tensile test specimen. That is why it has been told that yielding begins, it is considered that that component will also yield if at a particular point the shear stress reaches this value. That means corresponding to tensile test specimen. Okay, so this is what is the idea of the maximum shear stress. Here also you can see the actual situation is compared with the tensile test specimen yielding. So for a tension test specimen, first you find out what is the maximum shear stress. For the tensile test specimen, we know the maximum shear stress is equal to Sy by 2, right? So yielding begins when the maximum shear stress in a stress element exceeds Sy by 2. So if the maximum shear stress in a specimen which is under general kind of a loading, if the maximum shear stress is more than Sy by 2, then that material will yield or that material will fail according to maximum shear stress theory. So now if you remember that how can we find out for a general kind of a stress element what is the maximum shear stress. Here you see 3 Mohr circle, where let us consider that sigma 1, sigma 2 and sigma 3, these are the 3 principal stresses. Okay, so if sigma 1, sigma 2, sigma 3 are the 3 principal stresses, then we can draw these Mohr circles, 3 Mohr circles. And what is the maximum shear stress? Tell me. This is what is the maximum shear stress, right? Tau max. And what is its value? It is the radius of the big circle. And what is the diameter of the big circle? Here it is sigma 1, here it is sigma 3. So this diameter is sigma 1 minus sigma 3. That means maximum principal stress minus minimum principal stress. That is the diameter, that divided by 2 is what is the radius, or nothing but the maximum shear stress. So maximum shear stress is what? Sigma 1, which is basically the maximum principal stress, sigma 3, which is the minimum principal stress, divided by 2 will be the maximum shear stress. And according to this failure theory, is sigma 1 minus sigma 3 by 2, if that equal to Sy by 2, then material will start yielding, or that component will start yielding. Okay, and for the failure, this value must be greater than equal to Sy. Then the material fails. Okay, so this is the condition when the material fails. So if this is the condition, then material will fail. Okay, so if you consider the factor of safety, then what we do, sigma 1 minus sigma 3 is equal to Sy divided by factor of safety. Okay, so this is the way by which we can use this particular theory. Now consider instead of a general state of a stress, let us consider the plane stress condition. In a plane stress conditions, you first remember one thing, that sigma 1, sigma 2 and sigma 3, these are the notations used for the principal stresses in a ordered form. That means they are ordered principal stress. That means sigma 1 is greater than equal to sigma 2 greater than equal to sigma 3. So sigma 1 means the maximum principal stress, sigma 3 means the minimum principal stress. Okay, in case of a general state of stress, these are the principal stresses. Now for the plane stresses, sigma A and sigma B, these are the principal stresses which are non-zero principal stresses. Okay, so in case of a plane stress situation, you know that one of the principal stress is 0. So other two are non-zero principal stresses. Those are denoted by sigma A and sigma B. Okay, so for a plane stress situation, sigma A, sigma B are the two principal stresses, and assuming the case that sigma A is greater than sigma B, let us first assume that sigma A is greater than sigma B. If this is the situation, then we can create three different cases where sigma A greater than sigma B and both are positive. So case 2, we have considered sigma A is positive but sigma B is negative, and case 3, both are negative. So these three situations can occur, and in each of the cases, how will be the condition of failure theory according to maximum shear stress? Let us see. So if sigma A, sigma B both are positive and sigma A greater than sigma B, then what is sigma A? Definitely sigma A, sigma 1 is sigma A, and what is sigma 3? Sigma 3 is 0, because you know that in a plane stress situation, non-zero principal stresses are sigma A and sigma B, and sigma A is greater than sigma B, and remember other one is always 0 in case of a plane stress situation. Okay, these are the three values of sigma 1, sigma 2, sigma 3. But which one will be sigma 1, which one will be sigma 2, which one will be sigma 3, that depends upon their magnitude and the sign. Now see, so if this is the condition, then you just put that value of sigma 1 and sigma 3, you will get what is the condition coming. That is sigma 1 minus sigma 3 is Sy, sigma 3 is 0, so sigma 1 is sigma A, so sigma A is greater than equal to Sy. Okay, so this is what is the condition. Or if you consider this situation, you will get sigma A minus sigma B is greater than equal to Sy. Okay, because if you consider this situation, now sigma B become negative, so that means that will become sigma 3, because sigma 3 is the minimum principal stress, and sigma A will be sigma 1. So sigma 1 minus sigma 3 will be sigma A minus sigma B, which is greater than equal to Sy for the failure of the component. Okay, remember all these conditions are corresponding to failure of the component. Similarly for this situation, when both are negative. Now if we just plot this maximum shear stress theory in terms of sigma A and sigma B, that means here for the plane stress situation where with respect to principal stresses it has been plotted. So case 1 basically indicates this line that you can see, sigma A greater than is equal to Sy. That means if sigma A is more than that, that means outside this one, then the material will fail. So this is the failure region, and this is the safe region. So within this it is safe. Then sigma A minus sigma B is greater than equal to Sy. The equation of this straight line is this one. Okay, so this region is unsafe region or the failure region, and this one is the safe region. Remember, this is safe region. So the shaded region is the safe. This is the safe region or non-yield region. That means the safe region. It will not fail. This outside it will fail. Case 3 is this situation. Now the situation will be just reversed. If sigma B is greater than sigma A, then other curves you will get on the other three curves that you will get. Okay, so this is what is the boundary within which if the principal stresses are there, then the material will be safe, and outside it will not be safe. Okay, so how we use this particular theory of failure, you just suppose there is a component and this component is under combined loading. Because of that, what you have to do at a critical point where the stresses will be maximum, you find out the state of stress. That means it's normal and shear because of bending, torsion and all that. From that you find out what is the principal stresses. So once you know the principal stresses, then using that principal stresses, what you have to do, you calculate these values. You see that it is under which case. So if you find that your principal stresses, so let us consider it is a plane stress situation, then you plot that sigma A and sigma B, this coordinate you plot. So if you plot this, suppose that point is this one, that means your design is safe. That means under this load, this component is not going to fail. And what is that factor of safety? To find that factor of safety, what you do, you just extend a line from origin to where it cut this particular line or boundary. Then this length by this length will give you the factor of safety. Okay, so OB by OA is the factor of safety. This is what is the factor of safety, which we are symbolizing by N, factor of safety. Okay, so or you can find out simply by considering sigma, depending upon in which situation, that whether this one or this one or this one. Let us consider it is at this one, that means in the first coordinate, then it will be Sy by N. So sigma A is equal to Sy by N, and from that algebraically also you can find out N is equal to sigma Y by sigma A. Or if it is in this case, then N will be Sy by sigma A minus sigma B. Similarly, if it is in this case, so this divided by this. So in this way we can find out the factor of safety also. Okay, and if you find that it is outside this region, then this is not safe. Under this load, this component is not safe. In this way we use this maximum shear stress theory. Here you can see that some of the practical experimental data on the actual component and what is predicted according to maximum shear stress theory. You have seen that it is within that region that is safe, but here you can see the actual material fails in this region. In this region actual material fails. That means it is quite clear that maximum shear stress theory is quite conservative. Okay, you see it is quite conservative. Okay, and this is commonly used in many design situations. Okay, definitely for the ductile materials. Now distortion energy failure theory. So this failure theory is a very popular. Whenever no failure theory is actually suggested, we prefer this distortion energy theory. The distortion energy theory is a very useful theory, and in many cases this particular theory is used. This has many names like shear energy theory, von Mises theory, von Mises-Henke theory, octahedral shear stress theory. So all these, the results are same as the distortion energy theory. So first of all we have to understand what we mean by distortion energy theory. But before that we have to know that why we are going for another theory, distortion energy theory. The reason is that it is originated from the observation that ductile material stressed hydrostatically, that means if the equal principal stresses are acting, exhibited yield strengths greatly in excess of the expected values. That means if material is there and if you apply stresses on that material of equal amount from all the sides, okay, you know that hydrostatic force is like compressive force acting of the same magnitude from all directions. So if you do in such kind of a stress that in all directions the stresses are same and there is no shear, that means the principal stresses in all directions are same, then you find that material is not yielding as expected. Rather, theoretically it is infinite, but actually you will find it will yield at a very high value. So this particular observation definitely tells you that yielding is not occurring because of these principal stresses which are same in magnitude in all directions. Okay, so actually we can divide the strain energy into two parts. One is the hydrostatic volume changing energy, okay, because of that equal amount of stress acting in all directions, because of that volume will change. And another one is the angular distortion energy. Because of the force when you are applying, there is an angular distortion, and this angular distortion is actually responsible for the yielding of the material, and that is why it is required to find out this distortion energy. Okay, so we know that the total energy will be because of the general state of stress. Suppose this is the principal stresses for the general state of stress, and that can be divided into two parts. One is the average stress acting in all direction, that is same, which is like principal stresses which is same in all direction, which is called the hydrostatic component, and another one which is the distortion component, that means the remaining part. That means sigma 2 minus sigma average, sigma 1 minus sigma average, sigma 3 minus sigma average. So we can divide the general triaxial stress into hydrostatic component and distortion component. Now this portion is not mainly responsible for yielding, only this portion is responsible for yielding, and that is why we are going to look for this component only, because this is responsible for yielding, because this is our observation that by this kind of a force, this kind of a stress, we have observed that yielding is not occurring. Okay, yielding is occurring at a very high value. That means this is not responsible for yielding. That means this portion is responsible for yielding. Okay, so let us try to find out the distortion energy. So theory, that means the failure theory tells that yielding occurs, that means the failure occurs when distortion strain energy per unit volume reaches the distortion strain energy per unit volume for yield in simple tension or compression test of the same material. That means if the distortion strain energy per unit volume of a component because of a general loading reaches the distortion strain energy of the simple tension test specimen corresponding to yielding, then material starts, that particular component is assumed to be yield. Okay, this is what is the distortion energy failure criteria. So let us try to see that what is sigma average. The hydrostatic stress is what? This average of sigma 1, sigma 2 and sigma 3. Now strain energy per unit volume we can calculate. This is, remember, the strain energy per unit volume, the total strain energy per unit volume is half into stress into strain in all three directions. Since there is no shear, because these are principal stresses, so shear components or a strain energy corresponding to shear is absent. So half sigma 1 epsilon 1, sigma 2 epsilon 2, sigma 3 epsilon 3. Okay. So now let us find out what are the values of strain in terms of stresses. So stress-strain relationship according to Hooke's law, already we know that in a particular direction, epsilon x, suppose in x direction, it will be affected by these stresses in all three directions. That is 1 by E sigma x minus Poisson's ratio into sigma y plus sigma z. Similarly, in the y direction and z direction. Now this stress strain relationship, now if you consider for epsilon 1, so epsilon 1 will be what? 1 by E sigma 1 minus Poisson's ratio into sigma 2 plus sigma 3, and similarly for the epsilon 2 and epsilon 3. Now in terms of principal stresses, you can express the whole strain energy per unit volume. Okay, just putting the value of epsilon 1, epsilon 2 and epsilon 3 in terms of sigma 1, sigma 2, sigma 3. If you do that, fine, and simplify, you will get that the total strain energy per unit volume will be equal to 1 by 2E into sigma 1 square, sigma 2 square, sigma 3 square minus 2 into Poisson's ratio into sigma 1, sigma 2, sigma 2, sigma 3 and sigma 3, sigma 1. So we are in a position to calculate the total strain energy. Okay. So now let us try to find out what is the volumetric strain energy. That means because of the hydrostatic component, what is the amount of strain energy stored within the material. So volumetric strain energy can be calculated in the same expression by putting that sigma 1, sigma 2, sigma 3 all are same and equal to sigma average. If you put that sigma 1, sigma 2, sigma 3 all are same and that is equal to sigma average, then the strain energy per unit volume is nothing but the hydrostatic strain energy per unit volume. So in this way you just calculate what is the volumetric strain energy. Volumetric strain energy means the strain energy corresponding to only the hydrostatic component of stress. Okay. So now in place of sigma average, if you put that sigma average as sigma 1 plus sigma 2 plus sigma 3 by 3 that you have seen in this expression A, put that value of sigma average in that expression. Now in this expression, if you put the value of sigma average, then volumetric strain energy can be expressed in terms of the principal stresses. So if you do that, you will get the final expression UV is equal to 1 minus 2 nu. This nu is the Poisson's ratio divided by 6 E. E is the Young's modulus, and this is what is the expression that you get. So what you have got? You have got what is the volumetric strain energy. That means because of the hydrostatic component, you have seen the total strain energy. Then how you can find out the distortion strain energy? Simply U minus UV. Okay. So if you do that, distortion strain energy is equal to U minus UV. That means you have to subtract this expression from the expression of U, and you will get this final expression of distortion strain energy per unit volume. 1 plus nu divided by 3E into sigma 1 minus sigma 2 whole square, sigma 2 minus sigma 3 whole square, sigma 3 minus sigma 1 whole square by 2. So this is equation 5.8 is the expression of the distortion strain energy. So once you know the general expression of distortion strain energy, if sigma 1, sigma 2, sigma 3 are the principal stresses, you can easily find out any kind of stress situation what will be the distortion strain energy. So if we want to find out what will be the distortion strain energy for a simple tension test, that also we can find out, because in case of a simple tension test, what is sigma 1? Is sigma 1 is equal to Sy, and what is sigma 2 and sigma 3? Those two are 0. So if you put that value, you will get for simple tension test, distortion strain energy will be 1 plus nu by 3E into Sy square corresponding to yielding. Okay. So distortion strain energy corresponding to yielding in case of a tensile test, you can find out as 1 plus nu 3E Sy square. So what is the distortion energy failure criteria? That the distortion energy, strain energy produced in that particular component must be greater than equal to this component for corresponding to tensile test, then the material will fail. Okay, then the component will fail. So the expression. So 1 plus nu by 3 will cancel from both sides. So only thing that will remain is this square bracket term, whole to the power half is greater than equal to sy. And if you write in terms of factor of safety, then you just put this as equal to sy by factor of safety. Okay, so this is what is the distortion strain energy theory. Now distortion strain energy theory can be simplified as by considering this particular bracketed expression. This particular stress is given the name von Mises stress, sigma prime, symbolized by sigma prime. So if you can find out sigma prime, you just compare this sigma prime with sy. Okay, so your theory is basically sigma prime is equal to find out what is the yield strength of the material divided by factor of safety. Okay, if the von Mises stress is more than equal to sy, then the material will fail. This is what is the von Mises criteria or the distortion energy criteria, where what is von Mises stress is by this expression. For the plane stress situation, you just put the value of sigma A, sigma B and 0 in sigma 1, sigma 2 and sigma 3. You will get von Mises stress will become this. Okay, or in terms of XYZ components in 3 dimensions, von Mises stress will take this form. If you can remember, that definitely will help you. In terms of XYZ components for plane stress, you can write the von Mises stress. You can remember this formula. Otherwise, you have to draw the Mohr circle and you have to find out sigma A, sigma B. Okay, or if you can remember this one, definitely this will help you. Okay, so the whole point is here, find out the von Mises stress corresponding to the load, because of certain load on a machine component at a particular point. Definitely to find out the von Mises stress, first you have to calculate the principal stresses. Okay, so if you know the von Mises stress, you can find out, you can use this particular criteria by comparing this with the sy. Now if you plot it in terms of for a plane stress, if you plot it for the plane stress, so here you can see the distortion energy failure criteria simplified as sigma prime is greater than equal to sy, or in terms of factor of safety or design factor, you can write this. So if you just plot in case of if you just plot it, you will find that this will be an ellipse. Okay, and here you can see the dark line indicates the distortion energy theory, and this dotted line indicates the maximum shear stress theory that you have already seen, right? And if you see carefully that the experimental data are closely matching with the von Mises stress criteria or the distortion energy criteria, whereas the maximum shear stress criteria is quite conservative in nature. Okay, now for the pure shear loading, that means if a pure torsion is acting on a shaft, okay, in that case you know that the pure shear will come. So what will be the Mohr circle? If you remember, the Mohr circle will be like this. So what is the maximum shear stress? Tau max, right? Here it is sigma A and sigma B are opposite in sign of the same magnitude, and what is that magnitude? That is same as the tau max. Okay, that is what is the shear stress. So the sigma A and sigma B both are same in magnitude but opposite in direction, and their magnitude is same as tau. So if you simply put it in the expressions of in their expressions, and you will find that what is the condition for the pure shear loading, what is the condition for the So for the maximum shear stress theory, intersecting pure shear load line with failure line results in maximum. Here you can see what is this. This is shear strength. Okay, shear strength corresponding to yield is equal to 0.5 into SY. That means here this is what is the pure shear line. Okay, you can see, because this is the sigma A axis and this is sigma B axis. So for a pure shear, what you have seen, that sigma A is equal to tau and sigma B is equal to minus tau, right? So sigma A is tau, sigma B is equal to minus tau. So this point is at an angle 45 degree. This is tau, this is minus tau. So 45 degree line if you draw, it will cut the line here. So here from you can see what is the corresponding value. So you can get this value as 0.5 SY. We will get this value is SY. So this value is 0.5 SY. So this is what is the shear strength of the material corresponding to yield. Similarly, for the distortion energy theory, you have to extend it to this ellipse, and if you get this value, you will find this 0.577 SY. Or you can also derive it algebraically if you just put this in the expression of von Mises stress, considering sigma A and sigma B as tau and minus tau. Then you will get that SSY shear strength value as 0.577 of yield strength. So in case of maximum shear stress, you have seen it is 0.5 SY. In case of distortion energy, it is 0.577 SY. Now we'll see another theory, which is the Mohr theory. Now some materials have compressive strengths different from the tensile strength. Okay, so when compressive strengths are different from the tensile strength, then we use the Mohr theory. Okay, so we have seen initially maximum shear stress theory, then we have seen distortion energy theory. Remember, both these theories are applicable for the ductile materials, and this theory is applicable when SY, that means yield strength in tension, is same as yield strength in compression. Okay, but there are certain materials, those are ductile materials, but their yield strength in tension is different in yield strength in compression. Then we use ductile. For those materials we can use the Mohr theory. Okay, so we'll see that what is the Mohr theory. Mohr theory is based on three simple tests like tension test, compression test and shear test. If you do the tension test, then you will get a Mohr circle like this one that we have already seen. If you do the compression test, then this will be this one, because now S corresponding to tensile is smaller and S corresponding to compressive, let us consider, is larger. And if you do the shear test, then it will be symmetric with respect to the vertical axis like this. So three more circles you can draw corresponding to tension, compression and shear. Now if you draw a tangent to all these circles, a curved line, this envelope is what is the failure criteria. That means if the loading on a material is such, because of that at a particular point the stress point is such that if it is within this envelope, if the stress point or the state of stress is such that it is within this envelope, then it is safe, and if it is out of this envelope, then it is not safe. This is what is the Mohr theory. But it is very difficult to in analytically to represent this curved line of all these three circles, and that is why a simpler version, which is called the Coulomb Mohr theory, is considered, where only tensile and compressive, these two cases are considered. Shear is not considered. So here you can see these two dotted lines, one is corresponding to tensile, another one is corresponding to compressive, and then a tangent is drawn. That will be a straight line now. Okay, so now this is what is the new envelope, and if a stress point is within that envelope, then it is safe, and if it is outside it, then it is not safe. Okay, so this particular theory is called the Coulomb Mohr theory, which simplifies a linear failure envelope using only tension and compression test. Clear? Now, according to this theory, let us consider a particular state of stress is such that it is just on the verge of failure, and corresponding Mohr circle is, say, this one, this dark one, which is shaded, this circle, whose center is C2, okay, and radius is C2B2. Now you see that you can see that this is what is ST, this is what is minus SC. Remember, ST, SC, these are all strength values, these are always positive. Okay, so SC is a positive quantity, so if you write something negative, then you have to put a negative sign. But sigma 1, sigma 2, sigma 3, they may be positive, may be negative, so we do not know whether they are positive or negative. But when we write the strength values, remember, they are always written in a positive form. Okay, so what has been done basically here, these two triangles, actually these lines are drawn. Here you can see this C3B3, C2B2 drawn, and you just consider this triangle. Now consider this big triangle and this small triangle. These two are similar triangle, you can see, and we can write that this length that means, what is this length, tell me? This length will be B2C2, that means this total length minus from here to here, right? From here to here, what is the length? From here to here, the length is same as this one. So B2C2 minus B1C1. B1C1 is the radius of this circle, which is, you know, what? This is ST by 2, because ST is the diameter of this circle, because this is the tensile test, ST is the tensile yield strength. So this length is equal to B2C2 minus B1C1. Okay, so what is, and this length divided by this length. So this length divided by this length. What is this length? This length is this point minus this point. Okay, so what is that? That is simply sigma 1. What is this point? This point is, what is the coordinate of this point? Coordinate of this point is ST by 2, right? Because the total diameter is ST, so coordinate of this point is ST by 2. And what is the coordinate of this point, tell me? Coordinate of this point is, here it is sigma 1, here it is sigma 3, then what is the midpoint? Sigma 1 plus sigma 3 by 2. This is what is the midpoint. So this coordinate minus this coordinate is basically C1 C2. So that is what is this quantity. Okay, so in the upper side it is B2 C2. B2 C2 means this radius. Okay, this radius is what? For the inner circle. For the inner circle, what is this radius? That is sigma 1 minus sigma 3. This is what is the diameter divided by 2. So this is what is B2 C2. Okay, so here you can see B2 C2 minus the radius of this circle, that means ST by 2. And what is C1 C2? C1 C2 is this coordinate, that is ST by 2. This coordinate is ST by 2 minus this coordinate. This coordinate is average of sigma 1 and sigma 3. Okay, so sigma 1 plus sigma 3 by 2. So this ratio, that means this divided by this, this will be equal to this divided by this, because they are similar. So what is this? So this diameter is, this radius is SC by 2 minus ST by 2, because this minus this, and what is at the bottom? That is C1 C3. C1, that is ST by 2, and C3, that is minus SC by 2. So ST by 2 minus of minus SC by 2. Okay, so this is basically ST by 2 minus of minus SC by 2. So if you simplify this expression, you will get finally this, that is sigma 1 by ST minus sigma 3 by SC is equal to 1. So if you incorporate the factor of safety, then instead of 1 you have to write 1 by factor of safety. Okay, now so for ductile material where tensile and compressive strengths are different, we use their separate yield strengths for compressive and tensile strengths. For brittle materials, this Coulomb Mohr theory is also applicable, but in that case what we have to do, instead of yield strength we have to use the ultimate strength, because in case of brittle material there is no specific yield strength. Okay, in that case we have to use the ultimate strength as the design criteria. Okay, so here you can see this is what is the criteria. Now for the plane stress, we can again consider for sigma A, sigma B for 3 different cases, and accordingly we can create these cases. Now you can easily by the time you have understood that how we decide that which one is sigma 1, which one is sigma 3, remember one thing, that sigma 1 is greater than sigma 2 is greater than sigma 3. In this way you just remember. And for a plane stress situation, remember sigma A greater than sigma B. Okay, these are the two, and another one may be the 0. So these are the 3 stresses in case of a 3 principal stresses in case of plane stress situation. Now depending upon whether this is both are positive, both are negative, one is positive, another one is negative, accordingly the sigma 1, sigma 2, sigma 3 will change. So just you put those values and you will get these relations. Now if you plot in sigma A, sigma B axis for the plane stress situation, you will get this is for the case 1, this is for the case 2, and this is for the case 3. If sigma B greater than sigma A, then other 3 cases you will get. But here you see that this is the safe region, outside unsafe. The picture is quite similar to maximum shear stress theory. The only difference is that here you can see ST, that means the yield strength corresponding to tension is different from yield strength corresponding to compression, which is larger. Okay, here in this diagram. Now failure theories for brittle materials. you see that Coulomb Mohr theory is actually modified here, and this is what is called the modified Mohr theory. Okay, so here you can see that experimental data where the actual failure occurs, you see that Coulomb Mohr theory is quite conservative one. In the first quadrant it is matching, but in the fourth quadrant if you see that it is quite conservative. Okay, here are the actual experimental failure points, and here it is quite conservative. But if you see the other diagram where basically this point is corresponding to the same, this point is corresponding to the same as the S ultimate in tension. S ultimate in tension. Okay, so up to that basically it is straight considered in this way, and then from that point it is joined to compressive point. So in this way the Coulomb Mohr theory is modified, and this is called modified Mohr theory. And if you consider this particular diagram, then you see that actual failure points are quite matching. So modified theory is quite matching with the actual experimental data. Okay. Now maximum normal stress theory is a theory which is not generally used in practice, but historically this is a theory. That is why we are also learning it, but it is not actually used. Okay, that you have to remember. Why it is not used, that you will understand when you see the plot. Here it is this very simple, that if the failure occurs when the maximum principal stress in a stress element exceeds the strength of the material. Okay, so if sigma 1 greater than sigma ultimate, similarly for the plane stress element you can see this criteria. It is not very difficult to understand. If you see, if you just simply plot it, you find that this will be like this. And if you see the failure points, you will find that failure points are within that. That means it is not predicting properly. Okay, this is very much unsafe, because many points which are according to this theory is non-failure region, but actually will fail, specifically in this fourth quadrant. Anyway, brittle Coulomb Mohr failure theory that we have already seen is this one. That is very important for plane stress situation for 3 different cases. These are the theory, and here it is the modified Mohr. You can see that what we have done basically it is straight gone up to the minus S ultimate, and then it is connected here. Similarly it is done in the second quadrant also. Okay, so this value is same as S ultimate. Okay, for tensile, S ultimate for tensile, up to that much it is like normal stress, and then it is connected to this one. If you just give a mathematical form of that for the plane stress situation, you see these 4 situations and the failure criteria. You can see this will be the failure criteria. Okay, you can easily derive these things. I am not spending time on it. Now the selection of the failure criteria is very important, when to use which failure theory, and for that let us see this particular flow chart that will definitely help you to understand. So first thing is that you have to identify the material is ductile or brittle. So for that what you have to do, you have to check whether the fracture strain is more than 5% or not. If the fracture strain is more than 5%, that means it is ductile material. Now if it is no, then it is the brittle material. Now for the ductile material, then you have to check whether the yield strength in tension and compression are same or not. If it is not, then you have to use the ductile Coulomb Mohr theory. But if it is yes, if they are same, then you have 2 choices. If you want to use the conservative theory, then it is the maximum shear stress theory, and if you want to use better matching with the experimental data, then it is the distortion energy theory. On the other hand, in the brittle side, if you want to use a conservative, then you have to use the modified Mohr theory. If it is not conservative, then modified Mohr theory, and if it is conservative, then brittle Mohr theory. Okay. So now coming to a problem where basically a component is given and certain loading is given, and from that we have to use the failure criteria. So here the component, you can see the load is coming here, and you have to find out suppose at this point A, what is the stress acting first, then from that you will find out the principal stresses, then we will apply the theory. And it is known that it has a minimum yield strength of 560 megapascal and AISI 1035 steel, forged steel, so it is a ductile material, and you see the yield strength is 560. That means yield strength in tension and compression, they are same. Okay, so we can use either maximum shear stress theory or distortion energy theory. So we will apply both and we will see the results. Okay, so here you see that because of that this load, there will be a bending and torsion. So what will be the bending moment? You see that F is acting here, so definitely that will try to bend this, that will try to bend with respect to z axis. Okay, this particular member will bend with respect to z axis. So bending moment will occur, and we know how to find out the bending stress. That sigma x we can find out by 32 into m by pi dq. Okay, so this will be the value, and the bending moment you can easily calculate, because that will be what? This force, magnitude of this force multiplied by this length up to A. Okay, this length. So that has been done. Definitely we do not know what is F, so answer is in terms of F. Similarly, we can find out because of torsion what is the shear stress developed. Because of torsion, the shear stress developed will be according to this formula, you know, TR by J, and it will be 16T by pi dq. What is this torsional value? That F into this distance. Okay, so finally your torsion data is in terms of F again. The directions you will understand clearly. Here you can see, if you see the element from this side, where this is z axis, this is x axis, that means this particular upper plane is basically zx plane, and on this plane what kind of shear? Because of this torsion, the shear will act in this plane in this direction, so definitely in the other side, to balance it, it will act in the opposite direction. Now normal stress will act in this direction, that is clear. Now if you flip it, that means if you just put this particular zx in this, then this will be in this direction. Okay, I think this picture is now clear to you. So you know sigma x, you know tau zx, you know that sigma z is 0, sigma z is not there, so you can find out now the principal stresses. You know this value sigma z, sigma x, tau zx, so you can draw the Mohr circle, and from the Mohr circle you can see the center and the radius, so you can find out sigma a and sigma b. So once you know sigma a and sigma b, you can find out von Mises stress to apply the distortion strain energy theory. So see, it's with respect to sigma a and sigma b, you can find out the von Mises stress. It will be of this much. See, F is still there in the expression. Now if you apply the distortion energy failure theory, then von Mises stress will be equal to Sy by factor of safety. Consider factor of safety to be 1. Consider factor of safety to be 1. Then just at the time of yielding, sigma y prime is equal to Sy. So from that you can find out Sy is known to you, that was given for 560. So you can find out F, and that is coming 1.77 kilonewton. You can also use the maximum shear stress theory for that problem, and if you do that, you know, according to maximum shear stress theory, the sigma a, sigma b already you know, Sy you know, so you can find out F from this expression. and what you can see that maximum shear stress theory is much more conservative, because it is giving, if you compare with respect to this one, lesser value. Okay. Now consider the same problem, but instead of steel, now let us consider this is the cast iron. Okay, and the properties of the cast irons are given. Here you can see the cast iron is a brittle material, and its tensile strength, that means ultimate tensile strength and the ultimate compressive strength values are given. They are different. So for this problem we can use either Coulomb Mohr or modified Coulomb Mohr theory. Okay, so both you can use, and we'll see what are the results. Exactly in a similar way, you have to find out the bending stress and the shear because of torsion, and then find out the principal stresses either by Mohr circle or by using the formula. Then use the brittle Coulomb Mohr theory. You see that your sigma A and sigma B are satisfying this particular condition, that is, one is positive, another one is negative. Okay, so you have to use this particular formula to find out this, and we have considered here n is equal to 1. So from that you will get the value of f. Similarly, for the modified Mohr theory, you will find that your condition is satisfying this one, and this ratio is less than equal to 1. That is why this is the condition that you have to use, and considering n is equal to 1, you are getting f is equal to this. So here you see that Coulomb Mohr is more conservative. Okay, this one is more conservative. Thank you.